using the prover.
Yeah, for sure.
Needs to feed the M of fk plus x.
Okay, we're going to start the second session on WHIR, especially talking about the implementation, the performance, the engineering, and we're going to have Thomas help us entertain this session.
Yeah, so let's get started. So how I imagine the session, I don't know if Giacomo is here.
On his way back, okay.
No problem.
Does he know we're here?
Yeah, probably.
Here he is!
No, not yet, just after. So, in this session, we are going to try to talk about WHIR, its implementation, the details, and try to see how we can move forward and advance about different topics. So, just as the core architecture of the current repo, so we have a repo where we have basically all of the implementation of WHIR, including the primitives, the provers, the verifier. And we are currently trying to upstream that into Plonky 3 in order to maintain that as a public good, have more haze into the code and more performance optimization. So basically, I will let Giacomo explain you about WHIR just after that, because I will not explain the theory of WHIR with Giacomo in the room. Not alone, and alone, yeah, of course. So we have like this, we have basically one folder when we have all of the constraint system. Giacomo will explain you what it is, but basically it is some constraints that are then transformed into like a large eval-egg polynomial before going into the sum check. We have a prover folder also where you can find all of the prover logic, including everything round by round, the sum check calls, and everything around the prover up to the final generation of the proof. We have a verifier folder that contains all of the verifier logic that should be really fast after receiving a proof, with all of everything related to verifying the sum check, verifying the round by round thing, verifying the Merkle things. We have also like a committer dedicated file. This is at the beginning of the run, where the user just transmits a polynomial that needs to be committed in order to provide a witness that then is proven by the prover. We have a specific sum check protocol folder where we have everything related to the implementation of the sum check, all of the tricks, all of the tests, and we have also a poly folder when we have all of the primitives related to polynomials. So how do you define a multilinear polynomial? How do you define multilinear points? How do you evaluate the test and all of this? We have also a fiat shamir that is a transcript management things. We will have like maybe a short discussion today about this fiat shamir, how we can upstream that into Plonky 3 in the most possible efficient and secure way. So basically these are all of the small parts of WHIR implementation today. If we go to the polynomial representation, we still have like a coefficient file and a wavelet transform that is here to do the interaction and the transformation between the evaluation form and the coefficient form. So basically, you can just represent the multilinear polynomials as a vector of coefficient or as a vector of evaluation, and both can be exchanged. But at the beginning of the implementation, what we have done is that we have worked with the evaluation domain, and then each time we needed to do an FFT, then transform into the coefficient domain, and then go back to the evaluation domain. But we found recently like a kind of some tricks to completely remove the coefficient domain and just use the evaluation domain by having like a separate DFT that is currently implemented in a separate file as basically a copy-paste of Plonky's reversion, but just working on the evaluation domain. And
can I quickly ask you, like, what do you mean by that? Because, like, in principle, the DFT is kind of,
like the purpose of the DFT is kind of to change between from one form to the other, right? So
Yeah, but when you provide as an input the elements that you want to DFT, you can pass them as a coefficient of the multilinear polynomial or evaluation of the multilinear polynomial, and then the DFT do the secret sauce inside. This is not the problem of the DFT, this is the problem of the input that you provide of the DFT.
You can think of it about like basically you have the input data. You have the input data, which is a polynomial, but is a multilinear polynomial. And when we're doing the FFT is kind of like a univariate specific, and we haven't really deal. So we're taking just the data of the multilinear polynomial as the thing that we need to encode, but we also need to figure out what is the right representation of the multilinear to keep in our system. And for the sum check, we usually want to do, say, an evaluation. This is what we're doing. Yeah. And the encoding kind of like just takes the data, does an FFT, and then uses it. But it's kind of like, so there are different evaluations and coefficient form, let's say.
Yeah, because when you see like the FFT, that is the one we call from probably 3, just sees the polynomial as just sees the data as univariate things. This is this different problem. Yeah.
Okay, so compute 3 needs a multilinear FFT.
Univariate FFT.
What's the DFT that you mentioned?
It is the one maintained in our current repo that we plan to delete.
Okay.
But not from.
The DFT is always univariate.
Yeah.
Just that you take the data, which in the system is the coefficient for evaluation of a multilinear polynomial, but you just take it as a vector of length 2 to the n, and then I encode it with a univariate FFT. So the FFT itself is always univariate, just the data interpreted as multilinear.
Yeah. Please.
Yeah. I think this is also what people have been talking about, but for multilinear polynomials, you can think of the coefficients as the evaluation on the 0 infinity like hypercube. So that that you don't need to convert anything.
Yeah. And an important point to consider is that we have like a constraint system in the implementation with some statements, so you can see that Giacomo will explain more of the theoretical detail after, but like we have to have some equality constraints. That means at the beginning of your implementation, you have like your polynomial at certain point equal to a certain number, a lot of these constraints, and then you have to manage all of these statements and transform that into, so we have this, we just initialize the statement, and then we had some constraint points. That means that at this point I should have a certain evaluation, and then we combine all of these constraints into a big evaluation eval-egg polynomial that is then put into the DFT, into the sum check, sorry. And this part is a huge part currently of the implementation. If you run like a complete WHIR round by round, it represents like 25% of the cost, roughly. So this is a huge part. We are trying to optimize this. Then we have, yes.
The constraint system is not air.
No. This is just constraints in the sense of WHIR. This means like Giacomo will also explain it, but to replace basically the traditional like quotient things that you have in univariates. Here in this case, you just enforce the constraint directly as part of the protocol, and so you have like f of something equals something, f of something else equals something else, and this is what you have then to transform into pq polynomial. We have like the sum check module. In the sum check module, this is also a place where we want to improve a lot, because we have the standard sum check, but on the top of that we can have a bunch of optimizations such as like the univariate skip. This is a method like proposed by Angus Green, and the goal of this method is to do a lot of work at the beginning by skipping like n rounds, something like 5 or 7, and do a lot of work in the base field before switching to the extension field. for now we are trying to implement that and to find the proper way to do this, but we have also other tricks that are also studied by Lambda class guys with other possible optimization around this sum check. For now, this is a huge part that we can optimize with also SIMD instruction inside the sum check to perform some more operation efficiently. Yeah. Please.
Do you expect like the combination of the tricks to make some check more efficient to be trivial, or do you think that when these tricks are going to be combined together, it's going to present some hard challenges?
Yeah, I think that for now we have made almost all of the trivial change, I think, to the protocol. Then everything that remains will be kind of challenging. But I think that if we organize the code quite well, well tested, well documented, and with kind of nice modules, we can make that manageable. But for example, if we look at the universe skip, the universe skip is a good example of that, because it modifies the way that you see your hypercube things, and so the way that you see your polynomial as a whole, and so this modifies almost all of the code. Other optimizations such as the Bagad and HAL optimization that are studied by Lambda class guy are much less invasive because they don't modify the verifier. So yeah, some methods will be okay, some other will not. For example, if you think about SIMD optimization inside the sum check, this will require some per architecture hierarchy. This means that you will not apply the same instruction for Neon and for Linux stuff, for example. So you will have to deal with these various architectures. So yeah, low-level challenges, let us say, but yeah. So yeah, I will talk about the open problem. I have classified them a bit with different level, let us say. At the beginning, the less invasive one, and at the end, the more invasive one, probably. So we have primitive optimization. Basically, this means like finding a better way to evaluate a multilinear polynomials, finding a better way to do, for example, like a Merkle tree or something like that. So basic primitives optimization. Sum check optimization, this is very important in my opinion, because we will benefit from that both in the PCS, at the PCS level, but also at the PIOP level and on all the level of the stack. Better parallelization strategy, I think that sometimes we underestimate it, but parallelization is really tricky. When you don't play properly with the parameters, you have some threshold where the parallelization is no more efficient. Yeah, Jesse?
Actually, I have a question on that point. What is the bottleneck? Is it CPU or memory access? And have we made benchmarks, like what is the CPU utilization? What is the...
I think it's more CPU, yeah.
Okay.
Yeah, but we need also to investigate memory much, but more CPU. But yeah, no, yeah.
The issue is that when you benchmark and the bottleneck is memory, your CPU is still pegged to 100%. And for example, FFT is typically a memory-bound algorithm. And I don't know who said that it's hard to optimize or it's very optimized, but it might be true for big field, but for small field, we likely need to take into account L1 caches, L2 caches, etc. And this is done in FFTW for floating points, but I haven't seen any implementation for finite fields that actually are aware of cache hierarchy.
Yeah, I remember you sent me like a PR that was done on your repo about some guy like trying to optimize that, for example, to put the threshold with the aware of the L1 cache and different L1 cache, for example, for Mac or Linux, because all of the machines don't have the same L1 cache, and so you can play with that a bit. Yeah.
Yeah, I can also say, so at least in Pluggy 3, I think we've both put a lot of effort into the FFT, but I completely agree that like I think you could squeeze out a lot more performance just because memory management is a nightmare.
So So two examples that I implemented the bit reversal permutation with cache blocking, and I had 30% perf improvement on the x86 CPU. And another one is transposition. So if you do the naive transposition, and if you do two-dimensional cache blocking for matrices transposition, you can get a 10x improvement because transposition is a memory-bound algorithm. This is something that is usually not known in academia and not represented in papers.
One thing that was helpful for us is we benchmark.
There's a button on the bottom you can.
We benchmark, basically report the FFT time as a ratio with respect to the estimated time if you only did that number of multiplications. So if you just compute raw the number of multiplications required for the FFT, yeah, that's like a useful benchmark to basically see if your FFT is any good.
Yeah, very arithmetic taxes, you know?
Yeah.
It's similar to the teraflops
It's similar to the teraflops that you do for matrix multiplication, except that it's FFT flops, I guess.
Field time and field off, so yeah.
Sure, I'm just saying this as like a strategy to basically check if you're, like, if you have more to gain.
Do you know how close you got? Did you get close to 1 or?
I think so for certain parameters. I haven't. This was like an intern who did it. But
Yeah.
yeah, I guess very close.
I think the Pluggy 3 is a long way off 1, so yeah, definitely play something we can do.
Yeah, would be worth knowing this number.
Yeah, definitely. Yeah, so yeah, this is part of this better implementation strategy, definitely. Of course, like the DFT is very important. I don't know how much we can gain on the DFT. In my opinion, this was like very optimized for now. Yeah.
That might be maybe a garbage idea, but just when I was now thinking through WHIR, I mean, one of the costs for the DFT comes from that you do non-systematic encoding in each step. You have the first domain, right?
Mm-hmm.
Second domain is shifted and even blown up.
Mm-hmm.
So what makes WHIR non-linear time prover, loosely speaking, is you first do the folding over the smaller domain, and then you need to extrapolate. So 2 FFTs, one small, and then all the calls at FFTs to evaluate. So what about if you just take these values and do again non-systematic encoding? It is not WHIR protocol, but maybe something similar. So so the way you ask the new oracle outside is not by a point evaluation; it's more a coefficient in that thing. So I'm just putting this idea on the table. Maybe it's garbage because one has to be careful here.
Yeah.
But if
I need to think about
something like this works out, it would mean you could save at least a fraction of the FFT cost.
Yeah.
Maybe it's not depends on your concrete parameter. Maybe it's not worth it because you increase the redundancy each step, so it's more like only small fraction for computing the coefficients from the values. Or if you had the coefficients, how do you implement it actually? So do you keep in mind, like just on the univariate level?
Yeah.
You keep in mind the list of coefficients also beside.
Yeah.
And you do the folding just on the coefficients, and then you.
Yeah, we do that on the evaluation.
Okay, then my idea is
yeah.
Forget this. If you have it anyway, that's probably the better way anyway.
Yeah, we need to check back after this because we have also like a select trick that was proposed by Giacomo, where everything then will be played into the coefficient domain directly, and we will remove the eval DFT that we have right now. And so, yeah, at this time we need to maybe revisit what you just mentioned. Yeah.
Probably not. Probably not.
Need to think about this. I need to think about this. Yeah.
If we keep everything in the coefficients domain, can we still do SIMD in the sum check?
because CMD is very natural in the subject if it's on the evaluation domains, but will this still work on the coefficients? Yeah, I think so.
You can't multiply your dividers.
Yeah.
Like you want to be in the evaluation domain so you can multiply it.
Yeah, and so that's why for me the subject is more natural if we keep it in the evaluation domain to have CMD easy.
I think that this will not change.
For the encoding.
I think even more than the SIMD, right? If you have two polynomials, you want to multiply them.
Yeah.
That's nightmarish in the coefficients domain. It's trivial in the evaluations domain.
Yeah.
So I think we definitely want to live in the evaluations domain.
But
Okay, but you could keep also with the coefficients just for the sake of encoding.
Well, but then you have to do like throw in a lot of FFTs to jump back and forth, right?
because currently there is no coefficients at all. So yeah, currently
I mean,
we just
maybe
have
it's not worth it because it's memory plays a role, but currently, you start with your values over the evaluation domain. Don't talk about the hypercube.
Yeah.
Now. Thanks. So maybe first better to settle to make things clear. You use this version of WHIR where you identify hypercube values over the hypercube as univariate coefficients, as monomial coefficients, right?
Yeah.
Okay. So you take hypercube values, take them directly as coefficients, evaluate them over the evaluation domain for the code.
Yeah.
So now comes the first folding step.
Yeah.
So the thing is that we want to encode. It's not like Fry, where you just make the folding by value and get, which is a quite cheap operation.
Yeah.
No FFT involved, and you get the values of the random linear combination of odd and even over the smaller domain. Now, we could do that also if you forget about the coefficients, but then we need, for the extrapolation step, to increase redundancy. We need to first compute the gain coefficients, and then do the extrapolated values over the. So maybe it makes sense to keep.
I think currently what we're doing, we're keeping the coefficients, the multilinear, the evaluation that are interpreted as coefficients. The sum check will already need to fold them. So these are already,
so you have it.
So
That's
I
what
have
they say.
it, and then but we're already doing that, and then we are encoding those with FFT for the next round. So you always keep. You need to keep them around.
So you don't.
we don't
so you can skip one FFT step.
Exactly. We never do an inverse FFT to
Okay.
get back. Yeah.
Understood. Thanks.
Just a small thing, but if we suspect that there may be some problem with the cache, we can just measure it, like maybe add to the pipeline something that measure like how many cache miss we're having, and that's it. Because I think like going for a too theoretical approach, maybe it's not needed. Like faster to measure.
Definitely. And maybe we could have like at the end, first Giacomo, we talk about like a reminder about WHIR and everything, like so that you have a clear understanding, and then maybe 3 topics that we could keep for the end: the Fiat-Shamir maybe compatibility with Planck history. We discussed that a bit yesterday, but let's finalize the discussion here. Also, like Planck history integration, it's directly dependent on this, though, so this will flow naturally after that. And maybe a very last question that we could keep for the end: what could give like WHIR 2.0? Giacomo, please feel free.
Okay, amazing. So I think my plan is to give my plan is to write down like toy version of WHIR, like the simplest version of it, which contains some of the complexity. Then we can kind of like talk about what things right now there are easy gains to go on, what things are harder gains, and then we can